We have talked on this channel a number of times about the electromagnetic spectrum. I have covered infrared, gamma, and the radio parts of this spectrum. Today, we are here to talk about one you might be more familiar with, which is X-rays. This is Cup of Science Joe, and I would like to continue covering how we can use different wavelengths of light to learn more about our universe. X-rays were first observed and documented in 1895 by German scientist Wilhelm Conrad Roentgen. He discovered that firing streams of them through arms and hands created detailed images of the bones inside. This is how X-ray imaging in the medical field kind of started to come to be. This works because bones are dense and they absorb more X-rays than skin does. So if you have X-ray film on one side of you, and the X-rays are shot through you from the other side, the shadows of the bones are left on the X-ray film while the skin appears to be transparent. We now have a little bit of history on X-rays, and as I hinted at earlier, objects in space also emit them. Let's take a look at our sun for an initial example. Now, our sun's radiation peaks in the visual range, but as I covered in a past video, the area around the sun, known as the corona, is much hotter. It also primarily radiates in X-rays. So, a method we have of studying the corona involves scientists using data collected from X-ray detectors on satellites in orbits around Earth. This data allows them to see and record the energy that flows within the corona. When it comes to astronomical bodies emitting radiation, it is the physical temperature of the object that determines what wavelength it emits, with hotter objects emitting shorter wavelengths and colder objects emitting longer wavelengths. If we look at the electromagnetic spectrum, we see that X-rays are one of the shortest wavelengths there is. They span from 0.01 nanometers to 10 nanometers and are topped only by gamma rays in their shortness. I covered those in their own video, which I will try to put somewhere up here. So for an object to emit X-rays, it means it is likely millions of degrees Celsius. Some examples are pulsars, the accretion disk of black holes, and galactic supernova remnants. One thing to note about X-rays is that they are blocked by the Earth's atmosphere. So in order for us to properly study them, we must place telescopes with X-ray detectors above the atmosphere. Similar to gamma rays, X-rays are too high energy to reflect off of a mirror if they hit it head on. They would just power on through it like a bullet hitting a wall. This also takes into account their penetrating nature. Instead, the telescope focuses the X-rays onto the detector using grazing incandescent mirrors. We can think of this like the X-rays ricocheting off the mirrors and into the detector. Now, what are some things we've observed using these X-ray detectors? On Mars, NASA's exploration rover Spirit used X-rays to detect the spectral signatures of zinc and nickel in the Martian rocks. The piece of equipment that did this was called the Alpha Proton X-ray Spectrometer. This instrument uses two techniques, one to determine structure and another to determine composition. Both of these techniques work best for heavier elements such as metals. We can also view Earth's aurora in X-rays. Now, these aurora are created when solar storms from the sun eject clouds of energetic particles towards Earth. They create geomagnetic storms that sometimes result in the aurora. The charged particles that are caused by this can also energize electrons in the Earth's magnetosphere. These electrons then travel along Earth's magnetic field, eventually striking the ionosphere, causing the X-ray emissions that we can pick up. Have a look here at an image of our Earth's aurora in X-rays. And worry not, these X-rays are not dangerous to us because they end up getting absorbed by lower parts of the Earth's atmosphere. Let's go back to supernova and their remnants, which we mentioned earlier. The one I would like to mention here is Cassiopeia A. This one was imaged by 3 of NASA's great observatories, and data from each of these were combined to create this image here. The image we are looking at combined 3 different wavelengths: X-rays from the Chandra X-ray Space Telescope, the visual spectrum from the Hubble Space Telescope, and the infrared spectrum from the Spitzer Space Telescope. I like this example because it shows us how combining data gathered from different light sources can teach us more than each one individually could. Moving back to the X-ray data in this example, it revealed hot gases that are around 10 million degrees Celsius. These gases were created when ejected material from the supernova smashed into surrounding gas and dust at speeds of around 10 million miles per hour. What speed? That is really fast. I also want to talk a little bit more about the Chandra X-ray telescope that helped capture part of the image. This telescope was launched in 1999 and has been active ever since 2000, so for 24 years. It consists of 4 pairs of mirrors and their support structures. Because of the way the telescope captures and detects the X-rays, the mirrors must be smoothed to a few atoms, so it required an extreme amount of precision when being put together. On a larger scale, this is like making the Earth so smooth that the highest mountain was less than 2 meters tall. Also, because the X-rays ricochet, like I mentioned earlier, rather than being directly reflected off the mirrors need to be aligned nearly parallel to the incoming rays. This causes them to kind of look more like glass barrels rather than the dish shape most telescopes have. This is something I've mentioned before in past videos covering parts of the electromagnetic spectrum, but I find myself intrigued by just how much we can learn about our planet, our solar system, and other parts of our universe by looking at and combining wavelengths of light that sit outside the visual range, which is all our eyes are able to see. And I'm excited to see what ways and methods of observing and learning we discover next. I hope you learned something, and I implore you to step outside tonight and look towards the stars.